Well, this slide is only provocative. I want to say that at the end, I try to give a true definition. In this definition, there are several elements like climate, meteo, potential meteo, and the dynamic of these objects. But let me introduce first a few things. If I speak with a Greek mathematician like me about climate, what is climate? Climate is an invariant measure. Invariant measure from which you can compute expectation, probabilities, etc. Meteo or weather is something more variable at a short time scale. Many years ago, 30 years ago around, with Hans Crauel, we developed a definition of random attractor that was successful for mathematicians because it could be applied more or less to 400 different examples or something like that. But we didn't have in mind climate, except that Michael Gill later on used that definition and several times spoke with me about a possible definition of climate related to this random attractor. This was the origin for me of the interest in the attempt to give this definition. And through the years, I tried to refine a concept of climate and meteo, but of course is let me anticipate that I cannot embed the Klaus Hasselmann did in '76. He produced a new theory of climate, very interesting for a mathematician, and it doesn't fit with this definition. So I know perfectly that it's just an attempt and something for discussion, let's say. These pictures are to understand what classical dynamical system. This is the classical dynamical system when we perturb, either we perturb by a deterministic non-autonomous input or by a stochastic input, which is also non-autonomous, but slightly rather. And the idea is that still we have some concepts of dynamical system alive, like attraction, but in a sense, we have to do the attraction pull back, namely if we want to identify what attracts, we start in the past and we observe something. By the way, in this system, if we go on, it synchronizes, namely these two branches reduced to one. It has just to wait a sufficiently big fluctuation. When there is a sufficiently large fluctuation, it synchronizes and becomes, the attractor becomes a single point. But this is not important for our discussion. And this idea of a pullback is essentially embedded into geophysics from the beginning, let's say, from natural ideas. And this picture is just to compare that there is in climate data randomness, there is the idea of taking averages, there is a non-autonomy, a trend nowadays, also historically many times in the history of world, but especially nowadays there is a non-autonomy. There is some randomness at short time scale, for instance clouds, and we should try to put all these elements together into a framework of dynamical system and find a definition. So two elements are a rapidly fluctuating element of the story and a slowly varying element that could be clouds and CO2 concentration. And the purpose is to reach a complicated definition. Let me see the first elements of this story. Mathematically a metric space and a non-autonomous evolution operator on the metric space. So it means that is a law of transformation from one time to the other, which moves configuration. States is a more complicated concept, but configurations into configurations, and with the usual composition rules. In this case, I choose the strategy that the parameters Q and omega are additional parameters. They don't change together with the dynamic. As I said, omega is a rapidly fluctuating input and the other is a slowly fluctuating input. But let us see step by step the idea that comes out. This object is the meteodynamic. X, the metric space over which it evolves, can contain all informations of the configuration that you see, velocity, pressure, etc. The two parameters, as I already said, could have this meaning, for instance, concretely. And therefore, due to the fact that the CO2 emissions are non-autonomous, this evolution operator is non-autonomous. It's very important to have the non-autonomy. In addition, is random because the parameter omega is very fast varying. These are the features of this framework. Like this. No. Good. So here, take expected values. Expected values here is written in a very complicated mathematical manner, but essentially I take expected values of the previous evolution observed through observables. Phi is observable, and this expected value give me the Markov, the Fokker-Planck evolution, which acts on measures, if you want, states on measures. So, and this is also non-autonomous. So I have a Markov operator, with in which I have to emphasize the presence of two times in order to describe the non-autonomy. Non-autonomy comes from Q, from the slowly varying parameter of CO2, for instance. The random parameter is frozen, is averaged in this vision, and therefore I reached the dynamic of the two objects. The meteo or weather dynamic is the first one. The climate dynamic is the second one. So we have two elements of the story in this slide. And then we need these are the evolutions of climate and meteo. What is climate? Climate, as I said at the beginning, in the usual mind, is an invariant measure. But here, everything is moving. The climate today is changing every 10 years. We observe some change of climate. And so the climate is a measure which depends on time and is invariant by this Markov operator in this way. Fortunately, even if this relation appears very vague, there are existence and uniqueness results. So one can take a certain stochastic differential equation, define the associated Markov semigroups, even in infinite dimensions, so including Navier-Stokes and things like that, and prove existence and uniqueness of a family of measures, mu. It depends on Q and on time. They change on time, these measures, and they represent the climate which change very, very slowly, because very, very slowly. This is the idea. In addition, it may be nice to discuss this convergence to equilibrium. I just mentioned by passing this idea that namely these measures, namely the climate today or the climate in 100 years, can be understood in a pullback procedure as what comes out from evolving a natural measure at time zero, which time zero means minus infinity. And this is so is a sort of convergence to equilibrium in which today is the end and the beginning is minus infinity. And so now we have the meteo dynamic, that was the random dynamic, non-autonomous at the beginning. Mediated becomes the climate dynamic, and the climate itself is a measure which still may change in time. But we can apply this pullback procedure. So the pullback procedure I mentioned a second ago, even if it was not a fundamental element of the story, can be used to define the climate today as the result of a slow evolution of climates from the past. But we can also apply the fast meteor to initial objects. Initial always means, you see, the initial time s goes to minus infinity. So initial always means that we start very back in the past history. But the object here can be two objects. One topological, namely sets. We can start from sets and apply this very stochastic evolution of meteor to these sets, or measures again. So take a measure which may represent the bag measure, whatever could geometrically represent our degree of uncertainty and description of what does it mean almost surely or probability, etc. And evolving by the fast dynamic this object, we construct other objects. Topologically, we construct sets, omega limit sets, and if we take some union over the starting sets, at the end we get something which looks like an attractor. So the notation A is for the attractor, let's say. And otherwise, if we start from measure, we get measures. But in both cases, this object depends on the slow parameter Q and on the fast parameter omega. On the fast parameter omega also. So these are random measures and random sets. And this is where I met Michael Gill. So at the end of the story, sometime in 2 decades with Michael, sometime it emerged that this random attractor was the climate. But it was abandoned, this idea. So it's not what we think today. The climate is not the random attractor, even if it looks nice, but is the other. And this is the final definition. So the random attractor is the potential meteor, is the potential weather that we observe. I mean, that we could observe, what we could observe, in principle, because it's topological. It contains all the possible information depending on a strange topological set that could appear. But inside this topological object, there is a measure, hopefully a single one, corresponding to the usual axiom A, Sinner-Bowen measure, if possible, but of course in this framework it's very difficult to prove results like that. A measure which is random, depending on the slow parameter, and this measure is the meteor. The meteor really, in the true sense, when they say which is the temperature, and they declare us some confidence interval or something like that. So it is a measure, the meteor, but very rapidly changing in time and slowly changing due to the CO2. The CO2 and the clouds, etc., both contribute to the time dependence of the meteor. The measure mu q is the climate, and the dynamic was defined before. I'm going to complete with this slide. This slide is the most difficult one related to an open problem. In this view, what replaces invariant measure in the usual view of people of what is climate, what replaces invariant measure are these slowly varying measures. So the ergodic theorem now, if you want to say that something is ergodic in the sense that time averages converge, now the time average should be on a very short time with respect to the climate time. So with respect to the climate time, which is decades, the very short time of 1 year, 2 years, you have to take ergodic averages there. And so this is a complicated formula to say what could it mean, could it be an ergodic theorem in this framework. I cannot formalize this. I don't have theorems on that. It is true that climate is the average of meteor, but the average in the statistical sense. If I want the average in the sense of ergodic theory, this is something still not completely clarified. And if one has more time than 10 seconds, one can realize that it has to do in principle with the idea of statistical equilibrium of statistical mechanics, but with respect to time. This is something like you have time like space in this huge, in the small, you reach equilibrium very fast, but if you move a little bit aside, the average properties change. And this is the philosophy of all this story. And so I think that's the end. Thank you very much.
We recovered 4 minutes. So there are thank you. So there are other questions. I will arrive.
Yeah, thank you, Franco. I was wondering, can you say something about the corresponding stochastic equation or about the, say, Fokker-Planck equation for the corresponding measures?
Now I have to run back the microphone.
So if you take a stochastic equation, whatever it represents, Navier-Stokes, etc., the U is the solution map of the stochastic equation, the stochastic flow associated to the stochastic equation. So it maps initial condition, initial configuration in configuration at later time of this stochastic equation. P is precisely the solution of Fokker-Planck, meant as a map from initial condition of Fokker-Planck to final result of Fokker-Planck. So this is precisely stochastic.
Questions?
Sorry, so the pullback attractor, will this be somehow related to the support of the random measure mu q omega?
Yes, yes. That is a theorem. That is a theorem. The measure which represents the meteor is supported on the attractor A. The attractor may contain a lot of spurious informations that never will appear.
So what is the issue with this ergodic theorem you were mentioning? And you are saying it's just a conjecture. What is the issue? Is the issue that you have another time in there, the little t? Is that the problem, or what is the problem? Conceptually, I guess it's a problem, right?
Yes. When I formulate an ergodic theorem, I need an infinite time. Here, the time is stretched to infinitesimal time. Like in statistical mechanics, you have a set of molecules. Locally, it goes to equilibrium very fast. So locally, there is a Lavoisier numbers that is at work. But if you move observation there, the averages are different, etc., because there is heat which is flowing, for instance, something which is flowing. But locally is in equilibrium. And this is the same concept. Locally in time, there is a sort of average in time which produces the climate. The climate changes in time, and we should find a way to formulate an ergodic theorem on infinitesimal times with respect to something which fluctuates on this infinitesimal time that is 2 years. For climate, 2 years is infinitesimal time. On these 2 years, there is something which fluctuates hourly, which is the weather. And this hourly fluctuation should average to give us the climate. Intuitively, it's clear. I don't know how to write precisely a statement and a proof.
Questions? If there are no more questions, let's thank Franco again. And now we have